This is part one of the events conversation 4A to 412. I'm going to talk about a presentation that Karen Leung gave at the robotics seminar at Stanford. And I'm going to just dedicate the whole presentation, this whole episode for this one presentation because I think it's really crucial. So Karen is in the robot interaction space. She's an assistant professor at UW, and her academic lineage actually goes back to Marco Pavone, Stanford professor. He himself got his PhD in dynamic robotic planning back, way back at MIT. So just before ImageNet and everything. So back to Karen, I think her work is really, really important. It's very timely also because it fits into the launch of FSD at scale, the end-to-end learning concept. What she does is she quantifies safe robot interaction. That is her main contribution to the science community. What does it mean for a robot system to be safe? And with safe, by the way, we're not talking about this political, conversation about, safety of large language models and that kind of stuff. This is physical safety. It goes, it can be summarized actually in collision avoidance, but even that is an open question. So we're going to discuss the details, but this is one, like everything else in robotics and AI, once you start asking some basic questions, you end up in almost some philosophical, labyrinth of what does it mean to be safe, and who exactly is the agent here in a multi-agent framework? Who is responsible for which action? How do we relate guilt in accidents, for example? All kinds of questions come up. We have the trolley problem, which is not something Karen was talking about, but surely it's part of this conversation. So back to her presentation, she was presenting work that is building on her PhD thesis, which is about using an analytical framework for safety. In particular, it's the Hamilton-Jacobi reachability concept, which goes back to control theory. Think of it like if we use basic control theory, we have a translation matrix A, which translates an input, like a given set of actuators of a robot into a new state of actuators, and that translation matrix now incorporates Hamilton-Jacobi reachability matrix, if you will. So a bunch of variables that also account for the interaction between agents. So if we have a two-agent system, it's between agent one and agent two. In a multi-agent system, it's between multi-agents. This obviously, it looks like a game theoretic problem, and it is one. And if you go down the technical path here and the actual implementation and the engineering of these systems, you will come to something that looks like a Bellman equation, or actually the technical term is Hamilton-Jacobi-Bellman equation. These are all applications of the same concept, which again is a multi-agent problem which can be solved through dynamic programming. But most importantly, I think, again, Karen's contribution is about having an analytical framework that is also data-driven and learnable, which is important for safety. So in other words, you have an a priori analytical framework that can gauge the safety of a system. This is the Not Even Wrong podcast. It's April 13, 2024. This is Krim Delco. Since the last update, we're down 2%. The market's down 1.5%. For the year, we are down 19.2%. The market is up 6.2%. We're underperforming by 26%. So Karen Leung, she's the first in a series of presentations in the week 4A to 412 that we will discuss. I will dedicate this whole episode to her because it's obviously incredibly important for us. We are heavily invested in Tesla, in particular because of the full self-drive stack that they're building. And we are very excited about work like the Karen Leung is doing because she's exactly in that field. Her PhD, let me digress a little bit. I think it's important when we talk about these scientific presentations, it's always useful to look at the academic lineage of these people because it gives you a better understanding where they come from. So Karen got her PhD in the aeronautics division at Stanford. she was advised by Marco Pavone. He himself got his PhD at MIT about 15 years ago, where he worked on dynamic robot control. Now, back then, there was, control theory was still, if you look at sort of Jitendra Malik's presentation that I discussed in a few episodes ago, and we have control theory in the 60s and 70s, right? And then we have this divergence, control theory on the one hand and AI on the other hand. In other words, we have this analytical framework with fixed analytical solutions to solve dynamic processes, which is control theory. And then we have data-driven, neural net-driven, adaptive systems that are sort of encompassed by AI research. And I think Pavone's thesis probably is 80-90% control theory and maybe 10% AI. Karen is 50-50, and we're going, I don't know how far we're going to go to the data-driven situation. Maybe eventually it's all going to be data-driven, but there's also good reason to believe that we will still incorporate some symbolic knowledge, some higher abstract representation. In other words, we're going to have some a priori knowledge about systems, about interactions that might not be just data-driven or implicitly derived from data. But that's for another episode. Back to Karen's presentation again. So what she talks about is really, okay, how can we interact? We have a robot that interacts with agents, whether it's human or robot agents. And how can we build an analytical framework to a priori understand that interaction? And then can we quantify safety as in collision avoidance? Can we have an a priori system that can tell us how safe a system is? If we look at the Tesla or Waymo PR, when they talk about the safety of their system, they talk about interventions, right? And hopefully not accidents. Sometimes even that is being discussed, how many accidents per million miles, things like that, right? But the point, of course, is you can't launch a system like that and then hope that you won't have interventions or accidents. You want to have some sort of a priori analytical framework to gauge whether the system is actually safe. And this is what Karen's work is contributing to. So I would say there's 3 steps here. Quantify safety, so using the Hamilton-Jacobi reachability, which is, think about it like a matrix of parameters or variables that govern the interaction between agents. Then she's adding learnability to it. In other words, can we parametrize this matrix and learn it in the real world? What does actually learning mean in this context? In other words, what is the data that we need so a system like that can learn? And that's obviously 90% of the work. I mean, not to diminish the analytical work and the algorithmic work and the math behind all this, but the actual fundamental execution from an engineering perspective comes down to the data. What kind of data does Tesla use when they gauge risk and when they learn this Hamilton-Jacobi reachability? I don't know if they're using this particular concept, but I would think that they're probably using something very similar. Karen works for NVIDIA, so she's together with Marco working at NVIDIA in research, and we all know what NVIDIA is trying to do in the self-driving car space. That's, again, for a different episode in terms of why we think that probably NVIDIA has a lot of muscle, but doesn't really have the feet on the ground. They need something like a cooperation with Tesla, maybe, or something like that to actually make it work. But that's, again, for another episode. So back to Karen's work, again, this is incredibly important. I think one of the biggest, I got 2 very interesting inspirations from her presentation. One is there's some sort of Moravec paradox in the self-driving space, and that is that the hard things are easy and the easy things are hard. What do I mean with that? We have a multi-agent traffic scenario. Every day, I have it with my FSD 12.3 now here. here in Northern California, it's not as bad as LA, but it's pretty bad around San Jose, and it's super, super complex around San Francisco, not necessarily because we have so many highways and traffic, but it's, space is limited. So you have these scenarios where you merge on a lane with lots and lots of cars, lots of speed, lots of different lanes, different, directions, and shoulders, emergency lanes, police, all kinds of stuff happening. And it seems to me that the system's pretty good at these situations. So to use Karen's framework, we have this multi-agent Hamilton-Jacobi reachability matrix, and it seems like that the variables that it's using and the math that is required to solve the trajectory problem, or in other words, to solve the question, well, what should the robot do next, right? What's the next token prediction? I'm going to talk about this in a second, but let's just leave transformers away for a second. Okay, what should the actuators do right now, right? And then what should they do next? This problem seems to be solved at a very high dimensionality, very complex level. In other words, this reminds me of the chess example. So what we thought, when we humans drive with lots and lots of traffic around us, we get really nervous. It's time consuming. We start sweating, right? It's, lots of people even don't want to do it. I know people like that, they've been driving for decades. They're still afraid of traffic scenarios on highways with lots and lots of cars. Turns out that this actually seems to be an easy solution analytically and from a robotics perspective. And here's why. Number one, the robot can obviously do the math much faster, but much more importantly, I believe that there is, if you have the more agents you have in a lot of agent type scenario, it seems that the agents themselves are constraining themselves and the dimensionality gets reduced. This is my impression. It doesn't mean it's easy to drive on highways, particularly because of the speed. But speed is something computers are really good at. Speed, they're really good at. A computer can very quickly analyze a car coming from the left, from the right. There's another thing that a computer can do that humans struggle with, which is see in all kinds of direction at the same time. We can't do that. We haven't evolved to do that. We don't have eyes in the back and on the side, which is interesting why we don't have that, but we don't, right? We only have eyes in front. We have senses. We can sense stuff. I think we've all been in this sometimes uncomfortable scenario where we sit somewhere and we feel somebody's behind us. So we can see, feel these types of things. But clearly on a highway, I've been driving for decades now, accident-free, and I had one bump when I was young, but anyway, so okay, one bump. So back to the episode. It is stressful to have to look to your left, to have to look to your right, and to also incorporate the car in front of you and in the back of you. My Tesla can do all of that pretty easily. So that's why it looks to me that the hard problems that we have, we humans, which are physical constraints, we can't see everywhere and we can't do 3 or 4 math equations at the same time. I have to do the math in terms of how fast am I going? How fast is the car in front of me going? Is it going to stop for any reason? Is the car on my left or my right going faster than they should? All of this math is difficult to do, and therefore becomes. By the way, just as a tangent, I always ask myself a similar scenario. Let's say on a ski slope, on a beautiful sunny weekend in Tahoe, whether it's in Palisades or in Heavenly, there's thousands of people on the slope, right? Or maybe hundreds of people at one time. And if you look at this just from a bird's eye view, you might think, oh my gosh, this is a disaster. Accidents will happen, and they do happen, but much less than you might think. Another scenario, beautiful 6 to 8 foot wave day in Santa Cruz steamer lane. anybody who's been to Santa Cruz at Steamer Lane knows what I'm talking about. There are hundreds and hundreds of surfers going for that wave. Now, Steamer Lane's not that bad because there's several peaks there, so it's not as bad as Pleasure Point, with where the peaks tend to be concentrated. But anyway, that's inside baseball now. What I'm trying to say is we have lots of surfers, very few accidents. I would think that, again, in a multi-agent scenario, there's sort of a nonlinear evolution of complexity. Very few agents, not so hard, because with very few agents, we can do the math. We have one or two people that are driving down a highway or surfing or whatever. We can we have a sense for what they're going to do. And then we go into this territory where it becomes really complex. So like medium-sized agent population, and then we get to a larger size agent population, it becomes easier. Why? Because I think at some point, scale constrains everybody. So again, Moravec's paradox in self-driving: the hard things are easy, the easy things are hard. It's one of the inspirations I got from Karen. Now, just to sort of round up this presentation, in most recent work, Karen talks about transformer architectures. The way she looks at the human-robot interaction is very similar to what Jitendra Malik was talking about. So we have actuator observation tuples. We run massive transformer-based architectures in an unsupervised way, and then we have these transformation matrices that we learn through data. And hopefully we can, through enough training and data and compute, we can then develop next token prediction type trajectory planning with safety natively incorporated. So this is the key. So we can develop algorithms that have Karen's ideas inside the algorithm. In other words, you have, let's say, but what that means in practice is you have a Hamilton-Jacobi Bellman equation with a loss that incorporates collision avoidance and some sort of constraint that is not deviate from your current action, right? So what that means is I have my car's driving and I don't want to deviate. I don't want to slow down or change my lane. That's the constraint, but I also want to have collision avoidance. So at some point, I need to, let's say, change my lane, but I don't want to be overly conservative. That's the key. So she's working on those types of ideas. The links to the papers are in the show notes. As a summary, I think this is a beautiful, beautiful presentation for many reasons. It's when science and technology and entrepreneurship meet in the Venn diagram, that's the beauty. That's where we live at Orange Capital Partners, and we feel that the self-driving space is exactly at that point. To paraphrase one of the professors I also met this week from South Korea, the name eludes me right now, doesn't matter. He mentioned that there is a certain return on investment in robotics, that a threshold that needs to be overcome, because robotics is this field where people are a bit reluctant to jump on the bandwagon. That's true. So we have a little bit of that going on, but we believe that the return on investment here with self-drive is massive, because it just makes the driving experience so much more pleasurable, convenient, and most importantly safe. And Karen is working on that. So again, beautiful presentation. I spoke about the lineage. I spoke about her ideas. So data-driven safety concepts, analytical frameworks, a priori ability to assess the safety of a system. All of these things are critical if you talk about, let's say, FSD 12.3, which is fully end-to-end learned, which doesn't have explicit safety barriers inside the system. We don't want to hard code things. So if we don't want to hard code, then how can we have data-driven analytical tools? And again, Karen's ideas are definitely one way get there. By the way, now that I'm thinking just as a tangent, this could also be interesting for other types of safety. Let's say we have the kind of, the discrimination question in large language models. We could solve those in a similar way where we have data-driven analytical methods in sort of human model type interactions, and instead of having hard-coded explicit solutions. So this is just as a tangential idea. Thank you.